good? All right, excellent. Hope you had a nice weekend and a nice Monday actually too. So a few things up here. Homework 3 is due a week from today at 4:59 p.m. So before class. The reason is the first exam is actually a week from today. So the material on homework 3 is fair game for the test. So make sure that you complete that before the test. Okay. We'll talk about a lot of those problems today, and also, going forward. Email me Monday. We can talk about them as well. So the first test is on Wednesday. There is a practice test on Brightspace now. I'll show you where that is in just a minute. Actually, I'll show you where that is right now. So this is Brightspace, as you can see. If you go to Content, down here, there's actually something in the practice exam folder now. So it's this practice test. So you don't get any points for it or anything like that. It's just as a study guide. So you have it now. Take a look at it over the weekend. We'll actually go over it on Monday. So it is multiple choice, but you do have to show your work. So if you just go through and circle the answers on the test, you won't get any points. You do have to show your work. It's always a nice feeling, though, once you do the problem, you see the answer there, you can circle it. Okay, so it's there for you. No points. Study guide. For me, I use that as the actual kind of template for making the actual test. So I'll use that to go through and make the test. 13 questions. You get the entire time to do this. You make your own formula sheet. So a regular piece of paper like this. Front and back, put whatever you want on there. Formulas, example problems, write yourself a note of encouragement, whatever you want to do. So that's up to you to make your own formula sheet. Okay? Excellent. Any questions about the format of the test or anything like that? So it's there, you'll have it, you can take a look at it, hopefully you'll have a chance to look at it over the weekend. So we're not going to meet in person for the lab on Thursday. There's going to be a FET animation, and I'll make a little video for that tomorrow actually and let you know when it's available. So don't come here for the lab tomorrow because I won't be here. You don't have to do this tomorrow at 5 o'clock either. It's due a week from Thursday, so you can do it whenever you want to, this lab. It's a FET simulation, which you already saw it actually. You can put, there's a crate, you can put things on the crate, push it, measure the acceleration, things like that. So I'll make a video tomorrow, and then I'll let you know when that's up there as well. Okay, good. Any questions about the lab? All right, excellent. So if you watch the video that I put up on Monday, it's about chapter 4, most of chapter 4, not all of chapter 4. It's about Newton's first law. Any object in motion will stay in motion unless acted upon by a net outside force. So we'll do some problems that involve both Newton's first and second law to begin with today. And then Newton's second law is F is equal to ma. It seems simple enough, right? It's just 3 variables, F is equal to ma. The thing is, you can use it for so many different situations. That's what makes it hard. You use it for a whole bunch of different things. It is a vector equation, which means look at the x direction independent from the y direction. Okay? Were you able to find the video? Okay. The nice thing about those, you can go back and watch them if you missed something. Okay, so it's there for you. Take a look at it. If you missed where it's at, I'll show you in just a second. So same thing, table of contents. When I let you know they're there, I usually put them in the actual announcement. But videos, this is where they're all kept to. Like if you can't find it, you're looking. I know it was an announcement. I've been putting them all in this video module as well. And they pretty much just go in order. Chapter 2, class September 2nd, September 9th, and then this chapter 4 video that I put up on Monday. So looking ahead for the schedule, we don't meet in person tomorrow. You'll have information for the lab tomorrow. Next week, though, we will meet Monday and Wednesday. So Monday will be a review here. If you can't make it, there's going to be a video. I'll post it, that sort of thing. And then Wednesday is the actual test here. So it's an in-person test. Yep.
Last week's lab is tomorrow, right?
That is correct, yep. Yep. So if you haven't uploaded last week's lab, if you were Group B, then yep, do tomorrow. And if you have any questions about that, we can talk about that today as well. Okay, excellent. Any other questions? All right, good. So why don't we start with some problems then? Mastering physics. And let's see, the first one I wanted to talk about was number 6 here. So this one says, add a third force that will cause the object to remain at rest. Label the vector F3. So right now you've got an F1 and an F2. We want to put an F3 somewhere on this picture over here, and I'll scroll up in just a minute, so that this object represented by the dot doesn't go anywhere. Okay, so this looks kind of like this. I like this one because you can physically just move things around. To add a vector, you click this add button here. So to make this thing not move anymore, pretend somebody's pulling this way, somebody's pulling that way. To make this not move, the third vector is going to have to be the opposite direction. So if you were to take F1 and add it to F2, the one that will not make it move, F3, has got to be the opposite of F1 plus F2. And you can move these things around. I'm going to take F2 and actually move it up here. And then if I were to add F1 and F2 together graphically, it would be this vector, right? Going from the tail of F1 to the head of F2. That's what I would get if I add them together, but I want to have it go the opposite direction. So F1 plus F2 right now is this, heading that direction. So the one to make this thing not move would have to be the opposite of that. So it would have to go from here to here. So the reason I moved it around is so I can get a more accurate vector here. Oops, so let me add F3. And I'm going to start here and go over to about there. And I want this to be at 0 degrees. Okay, so that looks about like F1 plus F2. And then I can take it and move it over here. You got to put F2 back to where it belongs. And let's see if this will actually works. Before I do that though, so now you can kind of see if you're playing tug of war, if one person was pulling it this way, one was pulling it that way, if you added a third person here and they pulled like this, that would balance everything out. Okay, so hopefully I put them back to where they belong. Correct, okay, good. So you might have to play around with it a little bit. If you don't have it at 0 degrees, it might not work, that sort of thing. Okay, so that's a piece of information from Chapter 4, Balancing Forces. Chapter 5 is actually really similar. It just gets into this stuff in a little bit more detail. So for the first test, we won't cover all of Chapter 5, just the first couple of sections of Chapter 5, which really go right along with Chapter 4. All right, any questions on that one? Very good. Let me see the next one I wanted to see, 18. So a man pulling an empty wagon causes it to accelerate at 1.4 meters per second squared. So remember, Newton's second law, F is equal to ma. So a man pulling an empty wagon, it accelerates at 1.4 meters per second squared. What will the acceleration be if he pulls with the same force? Okay, same force when the wagon contains a child whose mass is 3 times as much as the wagon. Okay, so it's going to have to be less, right? Because the child's mass is more than just the wagon. So from F is equal to ma. we can solve this problem. Okay, F is equal to ma. So for a given force, the acceleration, they tell us, is 1.4 meters per second squared. So that's just for just the wagon that has a mass of m. That's kind of like the first situation. Now the second situation is, now it's the same force, how much is the acceleration for a different mass? So it's tempting to say that, well, this different mass is 3m, right? Because they tell you that the child is 3 times as much. But you can't forget that the child whose mass is 3 times as much is actually in the wagon. So the mass here is 4m. The wagon plus the child who is 3m. So the 4m is the wagon plus the child. So wagon plus the child. Good, so you go from a given force, given mass, the acceleration is 1.4. Now we have the same force, but the mass is 4 times as much. So if you make the mass 4 times as much, what do you have to do to the acceleration? Going to go down by a factor of 4, right? So same force, if the mass is 4 times as much, the acceleration is going to be 1/4 as much. Good. So 1.4 meters per second squared divided by 4. Like 0.35 maybe, something like that. Okay, good. So you might have different numbers for your problem. That's the way to do it, though. Know that for a given force, m times a is that force. Okay, good. Any questions on that one? All right, looking good so far. Number 21. Here's a graph, that you can't see. Here's a graph of acceleration versus force. Okay, so whenever you have a graph, again, first thing to do, look and see what's being graphed. What is the object's mass? Okay, same thing, Newton's second law still works here. We can pick out a nice convenient spot and see how these things are related to each other. You can pick out whatever you want to. It looks like from this picture, when you have 0.5 newtons, you have an acceleration of 2. So 0.5 newtons, that's what force is measured in here. On the actual graph, this is 2 meters per second squared. So use Newton's second law then to figure out what the mass is. And this makes sense too. The bigger the force, the bigger the acceleration. The slope here is actually what the mass turns out to be, right? F is equal to ma. So you can use this to figure out the mass. It turns out actually the slope isn't the mass. The inverse of the slope is the mass. I'll show you why that is in just a second. Whoops. Okay, so same thing, F is equal to ma. In the graph we said, well, a force of 0.5 newtons. The corresponding acceleration was 2. So then we could use Newton's second law, solve for the mass. So force divided by acceleration is the mass. Good, and we have the force, we have the acceleration. From the graph, you can pick whatever point you want. That was a nice convenient one though. So 0.5 newtons divided by 2 meters per second squared. So now don't forget, a newton is a kilogram meter per second squared. So the meter per second squareds cancel out and you're left with kilograms. Okay? So probably about 0.25 or so. All right, excellent. All right, any questions on that one? Yeah, so far so good with Newton's second law. You have to start somewhere. It's going to get trickier here in the near future. Okay. All right, so in this one, your car is accelerating to the right from a stop. Okay, very good. For the steps and strategies involved, you can watch this video tutor solution. So it's the author of the book working out a similar situation. Not the exact same, but similar. And we want to identify all the forces acting on the object and draw a free body diagram. So your car is accelerating to the right from a stop. Okay, so we'll have to, maybe we'll do it on a piece of paper and then come back and put it on this actual problem. Okay. So accelerating to the right means that there has to be a net force to the right from Newton's second law. Right, so if the acceleration is to the right, that means there has to be a net force to the right. So whatever force we have to the right has to be bigger than whatever force we have to the left. Up and down, though, these are actually equal to each other. Normal and weight. These two will be equal to each other, but the force going to the right has to be bigger than the force going to the left. That's because then we'll have a net force, and therefore we'll have an acceleration. Okay? So let's see what they're actually calling these things. Okay, good. So here's what we can add. Normal force, weight, drag force, and force of friction on the car. Now this is a little bit tricky because force of friction on the car, it seems like that would be the force that would be going the opposite direction, right? Well, pretend like I'm on ice here. So this is ice, and I want to walk this direction. So to walk this way, if I was completely with no friction, I would just do this. I wouldn't be able to walk, right? If this was really ice and I had literally had no friction, I would not be able to walk the way I normally do. So it's the friction, actually, it's the friction on my shoe that keeps my foot from just sliding back. So I would just keep doing this if there were no friction. So there's friction on my foot that keeps my foot from going this way. So my foot is trying to go back this way. It's the frictional force that actually lets me go forward. So I can actually walk this way. Friction on my foot is going this way, the same way that I'm moving. If not, my foot would slide out. So that's the force that has to be bigger to the right. This frictional force on the car is the one that actually propels it forward. So pretend that you're in your car. Sorry to bring this up, but it's going to be winter soon, right? And it's going to be icy. So if you're in your car and you're trying to go forward and you're on ice, you might not be able to move. You have to have some friction that stops the tire from just spinning like this to propel you forward. It's a little tricky. Usually you think of friction being the opposite direction that you're moving, but in this case it actually is the force that lets you go forward. So that's going to be the one that's going to be here. And it's going to have to be bigger than the drag force. We don't know exactly how much, but, whoops. Trying to see why it won't let me add it. Let's see. Oh, I guess I changed the name of this accidentally. All right, so I accidentally changed that to drag force. There we go. That's the drag force back the other way. I want to add friction. And that's the one that's going to have to be this way at 0 degrees. I could move it around a little bit. Okay, so that's bigger than the drag force. Then I could add the normal force. And this is the one that has to be straight up and down. And then I want to add the weight. So the weight and the normal force should be equal to each other. I don't believe mastering physics actually makes them be exactly the same. But you definitely have to have the frictional force bigger than the drag force. Okay, good. So this will give me an acceleration to the right, up and down forces, the normal and the weight balanced. Okay, any comments before I hit submit? We'll see if it works out. All right, good. Excellent. So this is a free body diagram that you just saw, and it is really helpful in solving a lot of different problems. Okay. And let's see. All right, good. So that's the sort of problems that you saw in homework 3. We still have some more to do, but we need a little bit more background information. So I want to show you the rest of the Chapter 4 PowerPoint, actually. Any questions on any of the other homework ones? I don't know if you had a chance to look at them yet. If not, there's still time, right? The test is not for another week, so definitely when you come to class Monday, have had most of the homework done. We'll talk about all the sorts of problems that are on the homework today. Okay. And we've got Newton's third law to talk about. All right, so we've seen the first 2 laws. Of the 3 laws, only one of them actually has a formula. The first one and the third one help you solve some problems. So Newton's third law, motion often involves 2 or more interacting objects, like in this picture, a hammer and a nail. It could be a truck going down the road and a mosquito, whatever you're talking about. A bat and a ball with baseball, or a foot and a soccer ball, Earth and moon. There's always interacting objects. So if you're talking about a force, there's always an equal and opposite force. So for example, if I'm leaning against the board like this, there's a force on the board from me, but there's also a force on me from the board. Those are equal and opposite to each other. So forces always come in pairs, and they're always equal to each other in magnitude, but opposite in direction. So you might say, that can't be true. I mean, if I hit the nail with the hammer, the nail goes this way. The nail gets the worst, maybe, of that interaction. How could the forces be the same? Well, the hammer is so much bigger than the nail, the hammer doesn't care. Like if a truck's going down the highway and hits a mosquito, it's the same force on a mosquito as the truck. It's just the truck is so much more massive, it doesn't experience the force in the same way as the mosquito would. But it still is the same magnitude of force. Okay, so this will help us solve some problems. So here's a couple of blocks. So an interaction is the mutual influence of 2 objects on each other. What does that mean? Well, there's a force between them. So if these 2 blocks are in contact with each other, and I'm trying to get these things to move, maybe I push on either A or B, get them to move, there's a normal force between these blocks. That normal force is equal in magnitude, but opposite in direction. So there's a force from B on A, and that's equal to the force from A on B. So that's a third law pair between those. Just like I pushed on the whiteboard, it pushed back on me. If you're pushing these 2 boxes together, there's a force between them. Normal force in this case, equal and opposite. Okay? So every force occurs as one member of an action-reaction pair. So they're always equal and opposite. Just like the hammer and nail example, I want to show this box example to you. Okay, document camera. Okay, good. So let's pretend we've got these 2 boxes. This is 5 kilograms. This is 10 kilograms. And I'm going to put an outside force here. I'll just call it force applied of 30 newtons. And this is kind of on a frictionless surface. And the acceleration turns out to be, of the system, 2 meters per second squared. So these boxes move together. The outside force is 30 newtons. The acceleration of the crates, whatever it is, boxes, 2 meters per second squared. What I want to know is, what is the force of the 5 on the 10? So I want to know the normal force from the 5 on the 10. I also want to know the normal force from the 10 on the 5. I should have called them A and B instead of 5 and 10, but you get the idea. I want to know how much this is and how much this is. Okay? It turns out that they're equal to each other, so if I find one, I know how much the other one is. So I can start using my free body skills that I've just learned about this week. So let me do the free body diagram of the 5 kilogram mass and also the free body diagram of the 10 kilogram mass. And I'll also use Newton's second law to do this problem. So for the 5 kilogram mass, just to be complete, there's the normal force, here's the weight. I have this 30 Newton force this way, and then I also have this normal from 10 on 5, right? That goes back the other way. They're in contact with each other, so we've got that normal force. I drew the 30 bigger than the normal from 10 on 5 because it actually is accelerating to the right. I could also do the free body diagram for this 10 kilogram mass. Same thing, normal, weight. That's the weight of the 10, that's the normal force on the 10. And then really what gets this one going is the normal from 5 on 10. I mean, really they're distinct objects, and maybe you want to try to think of them as a system, but I'm just breaking it down looking at the actual forces on the 5 and the actual forces on the 10. And then hopefully from this, using Newton's second law, I can figure out the normal from 10 on 5 and the normal from 5 on 10. They should be equal to each other, opposite directions. Okay, so let's actually do that and see what we get. So for the 5 kilogram one, F is equal to the 5 kilogram mass times the acceleration. That's always going to be true for us. And then I can do the same thing for the 10 kilogram. The net force, the 10 kilogram mass times the acceleration. And then it's up to me to put whatever's going to be in this dotted box here. So this is Newton's second law. This is perfectly good. Whatever I put in the box is going to come from this picture. Newton's second law, that's going to be always good for us. Whatever goes in this box comes from the picture. So these are the actual forces. This net force is what you get when you actually add them together. Same thing over here. So let me put these numbers in here. I can write 30 newtons minus normal from 10 on 5. These are the actual forces. 30 newtons to the right, and then we don't know how much it is yet, but it's back to the left. These are the actual forces. For the 10 kilogram mass, the only one that we have, nothing is back the other way because there's no friction. We've got the normal from 5 on 10. Okay? I might as well finish this one off because right now I can put these numbers in. This would be 10 kilograms, 2 meters per second squared. This is 20 newtons. That's the normal from 5 on 10. Okay, so hopefully you can see that okay. Scoot it up a little bit. So now the drama is building. This has to be the same as this, right? Just opposite direction. So we'll have to do a little bit of algebra to the left-hand side one, but we could do that. So let me put normal from 10 on 5 over to the left, move mass 5a over to the right. So when I do that, I get normal 10 on 5. So I've moved it over to the left-hand side. 30 newtons minus m5 times a. Okay. Hopefully I haven't messed up the math at all. We'll see in a minute. So this would be 30 newtons minus 5 kilograms times 2 meters per second squared, or 20 newtons. Same thing, right? So this is the same as this. That's the normal force between them. It had to come out to be the same, and you can see that it is. So let's take a step back and think of this whole thing as kind of a system. Here. So we really have 30 newtons of outside force to work with. The way to think about this is the net force on this one is 20. The net force on this one is 10, right? 30 minus 20. The net force on this one is 10. The net force on this one is 20. That's how really the 30 newtons gets distributed between the two of them. Now, if it turns out, and this might not, to me it doesn't seem like it would matter which way you applied the force, but if you put the 30 newtons this way instead of this way, it's a completely different normal force between them. So if you flip that 30 newtons and applied it to the 10 kilogram box, you get a completely different normal force between them. So it matters the order here that the boxes are stacked. Okay. All right, good. Any questions on this one? All right, very nice. So I thought we could take a look at problem 4.43 then. So this homework 3 has 14 questions. 8 of them, which you can't see yet, 8 of them are from chapter 4, and 6 of them are from chapter 5, but they're really related to each other. There's a lot of overlapping between chapter 4 and chapter 5. So let's look at 43 here. So we've got 3 skaters, numbered 1, 2, and 3, stand in a line, each with their hands on the shoulders of the skater in front. So skater 3 at the rear pushes forward on skater 2, and assume the ice is frictionless. We want to draw the free body diagram of skater 2. So we got 1, 2, 3 in a line, each with their hands on the shoulders in front. 3 is at the rear, pushes on skater 2. Assume frictionless ice. Okay, so I guess it's kind of like, and you tell me if this is how you're interpreting it. This is 3, this is 2, and this is 1. Other way around? Oh, sorry. Okay, so I'm thinking it's like this, right? 2 is in the middle, and 3 is on the end. Skater 3 at the rear pushes on skater 2. Assume ice is frictionless. Draw the free body diagram for skater 2 in the middle. Okay? Excellent. I guess I'm trying to think, do I have 1 and 3 mixed around? But I think that's okay. Okay, so we got to draw the free body diagram of the skater in the middle. So really, they're all in contact with 3 is in contact with 2, because 3 is pushing on 2, but 2 is also pushing back on 3, just like I'm pushing on the board, right? And it's pushing back on me. So pretend there's a skater in front of me. If I'm trying to push the skater this way, the back of this middle skater is pushing back on me. I mean, not with their hands, but with their back. If I went up to skater 2 in the middle, and we were both on ice, I pushed skater 2 that way, what would happen to me? So totally we're on ice. I push skater 2 that way. What happens to me? I would go this way. So what's making me go back this way? It's the force from 2 on to me. Even though like the skater doesn't turn around and literally push me, I push on the skater. There's a force on the skater from me, but there's a force on me from the skater. That's what gets me going back the other way. So although skater 2 is not actively pushing me, the act of me pushing on 2 repels me back the other direction. Okay, so we want to do the free body diagram of skater 2. So keep that in mind. Well, there's the normal force onto the force of gravity on 2, but there's also this normal force from 3 on 2. That's the push from 3 onto 2, but there's also a normal force from 1 on 2, back the other way, right? This is the one that you might think this isn't really an active force. 1 doesn't turn around and push on 2, but it's the active 2 pushing on 1, 1 automatically pushes back on 2. Okay? These are called normal forces because they're, contact forces. So let's go back to mastering physics. Whoops. Yes, and we can add these things. Draw the vector starting at the black dot. The location and orientation will be graded. The length of the vectors will not be graded. Okay. Okay, so they're not calling it a normal force. Really, it's a normal force. They're calling it normal force from skater 1 on skater 2. And then this one is the contact force, which usually we would call those normal. They're just calling them like a generic force F. And then there's the weight. So I'll add an easier one to begin with. So we want this to be at 90 degrees. And then I could add the weight. That's going to be straight down. And then I could add this contact force from 1. So this is the force from 1 onto 2. That's the one that goes back this direction. Okay. And then finally, the force from 3 onto to 2. Okay? And again, they're not grading. We don't know how big they are relative to each other. It's just the direction and orientation. Any questions about that before I submit? All right. Excellent. Good. So free body diagrams could really help us solve these problems. Okay. Comments? Questions? Okay. So let's see a little bit more with chapter 5. So really it's, some books don't have a separate chapter 4 and chapter 5. It's just one chapter. So so just letting you know, they're really, really related to each other. So for the test, make sure you look through the first, I think, 3 sections or so. It gets into a lot more detail once you get to the friction section. So we'll do this friction section after the first test. So applying Newton's laws. So we use Newton's laws to solve problems. Again, only one of them actually has a formula. The other 2 just are useful to help you solve problems. So you learn different expressions for different forces we've seen, weight, normal, things like that. You learn how to balance weight and drag force, leads to the maximum speed, something called terminal velocity. So a boy is pushing as hard as he can, but the sofa isn't going anywhere. So this is equilibrium. So equilibrium doesn't mean no forces, it just means there's no net force. It's kind of like Newton's first law, really. There's no net force. Forces are balanced. So this can be one of 2 things. Equilibrium either means the object's not moving, that's the first thing it means, or it could mean that it's moving at a constant velocity. So constant velocity, you can have a lot of forces on something moving with the constant velocity, but there's no net force. Okay, so really Newton's first law, that's what they're talking about there, no net force. Okay. Newton's laws also allow us to relate forces to dynamics problems. So now dynamics problems mean there is a net force. So if there is a net force, then we know there is an acceleration. Okay, so you've got equilibrium problems, sometimes called statics problems. There's whole classes on statics, by the way. Maybe you've actually taken one. Balancing forces and torques. You might have taken a statics class. Or you might have even taken a dynamics class where you just work on problems where you have, where you do have a net force. So the skier here is picking up speed, going faster and faster. So for that to happen, you have to have an acceleration. And for you to have an acceleration, you have to have a net force. And we'll definitely be using free body diagrams in this chapter. Okay, good. So equilibrium just means the forces are balanced. Later on, when we do things that rotate, we'll have forces and torques being balanced. But for the meantime, nothing's rotating, we're just balancing forces. This is a fancy way of saying all the forces are balanced. When you add them all up, this means add up all the forces, they add up to 0. It doesn't mean there's no forces, it just means whatever is to the right is balanced by whatever's to the left. The y direction means whatever's up is equal to whatever's down. Okay. Orangutan weighs 500 newtons, that's the weight, hangs from a vertical rope. What is the tension? So just hanging around like this, not going anywhere, no net force, whatever's down has to be balanced by whatever's up. So if you got 500 newtons down, then you have to have 500 newtons up. So this is a statics problem, we're just balancing forces. It's just a one-dimensional problem too, right? There's just up and down. So the answer is 500 newtons, that's what the tension's got to be. Okay. Here's another example we can take a look at. A car with mass 1,500 kilograms is being towed at a steady speed. Okay, so that means the acceleration is 0. That's what you have to bring to the problem. Steady speed means there is no acceleration. There's no net force. Definitely forces, just no net force. Okay, steady speed, rope at 20 degrees from the horizontal, like in the picture. We have a frictional force of 320 newtons. That would be back to the left. We want to know how much is the tension in the rope. So you knew it was going to get a little trickier, right? This we got tension at some kind of angle here. So we'll have to use our breaking into components idea for this problem. So there's the picture. There's what we know. And we're trying to figure out the tension. So there's the free body diagram at the bottom down here. Normal force. Here's the weight. Here's friction going back the other way. And here's tension. Now this tension has a part in the x direction and a part in the y direction. So you might look at the picture and say, okay, well here's the weight. The normal force is not drawn as big as the weight. Why is that? Well, it's because whatever's down has to be equal to all of the forces that are up. So down we have weight, but up we have normal, and we also have tension in the y. So if you took the normal force and added it to the tension in the y, that would add up to the weight. In a way, you're kind of like, as you pull this, kind of lifting up on the car, right? Because there's a part of this in the y direction. So that helps out the normal force. The normal force doesn't have to be as big. Now in the x direction, we've got friction back to the left. It's going to have to be equal to the tension in the x direction. So this is the picture after you already get the car moving. So if it started at rest, this would have to be a lot bigger, right, to get it to move in the first place. We're just looking at the picture after it's already moving and you have it moving at a constant speed. So right now it's moving at a constant speed. Good, so we want to figure out how much this tension is. All right, good. So we have a 1,500 kilogram car. We know the angle, 20 degrees, and the frictional force is 320 newtons. And we're trying to figure out the tension. And this was the free body diagram. Normal, weight, here's the tension. Here is really the tension in the x direction, tension in the y direction. And then we've got this frictional force, 320 newtons. Okay. So I know that the tension in the x direction has to be 320 newtons. So how do I know that? Well, there's no net force, right? Constant speed, acceleration 0. Whatever's to the right has to be equal to whatever's to the left. They tell me what's to the left, 320 newtons. That has to be equal to whatever's to the right, tension in the x, 320 newtons. Okay? That doesn't actually answer the question. They want the overall tension. We can get it several different ways, though. We know that this angle is 20 degrees. So we can do a little bit of algebra. Doesn't look so great. Oh, so theta is 20 degrees up there. I can use a little bit of trig to get the overall tension. So you're looking at this picture. We got an angle and a side. We want to get the hypotenuse. So you've got sine, cosine, tangent. You know, what are you going to use? You just got to try it out. Now, if I tried to use the sine of theta, that would involve ty. And I don't know what ty is, and I don't know what t is. So I'm not going to use the sine. I'm going to use the cosine of theta. Let's see if that works for me. So cosine of theta would be the adjacent side over the hypotenuse. And that will actually work because I know theta, I know tx from the physics of the problem. The only thing I don't know is t. So let me multiply both sides by t, divide both sides by the cosine of theta. Okay? So if you take 320, see how this looks? Oh, all right. I think I told you I found my calculator, but I actually remembered to bring it today. So I'm taking 320, that's t in the x, divided by the cosine of 20. My calculator's already in degree mode. So 340.5. So maybe 341 newtons if I wanted to round to the nearest digit there. So the tension in the x direction was 320. The overall tension is 341 though. If I wanted to, I could figure out ty, right, at this point. They don't ask for it, but I could. I know this side, I know the angle, so I can get ty if I wanted to also. Is ty 21 newtons? How did I get that? 341 minus 320. Seems like, oh, that's a good guess. You know, maybe it is. It turns out, let's actually figure out what ty is. So now that we know that the overall tension is 341, I could say that the sine of theta is ty over t. So t times the sine of theta is ty. So this would be 341 newtons sine of 20. Okay, so 341. I should have just used the whole thing, right? 340.5368872 times the sine of 20. 116. So remember when you're looking at these vectors and you break them into components, the 341 that we had is in components. You know, you can't just add them together. You can't just literally add the x part and the y part together. You have to add them. X part squared plus y part squared is the other part squared. Okay? So that was a little just illustration of that idea. Okay? Good? Any questions on this one? While we're at it, just one more thing. Because we have everything now, right? No, we can't do that yet. Okay, we'll just leave it at that. Any questions, though? All right, excellent. So that was towing a car, and we solved that problem that you can't see. All right, good. So a ring seen from above, so this is the overhead bird's eye view of what's going on here. The ring is not moving. How big is this force? So let me get us started on this one. New piece of paper. So again, this is an overhead view of what's going on. So I'm just going to represent the ring as a dot here. This is 10 newtons, theta, also 10 newtons, same theta, and then this force is here. So I'm going to call this T, 10 newtons, T. Okay. So this ring isn't going anywhere. So the net force is zero. It's equilibrium, right? The forces are balanced. The one we just did, constant velocity forces were balanced. This is one where it's not moving. Forces are balanced. So whatever's up has to be equal to whatever's down. So if you think about this T as having a y part, and this one having a y part, there's two of them. Two TYs, right? Those from each of them. Two TYs is equal to this force. That's what's balancing this thing. Let me just see if there's a... Okay. So that's the autofocus button. Okay, there, that's better. Excellent. So there's two components of the tension that's up because you got this one and this one. That's got to be equal to the force that's down. This is perfectly good. It's just not in the form of the question on your PowerPoint, right? So let me go back to that actually. Right? It doesn't look like any of these answers. It turns out it's going to give us this. We can just do a little bit of work with this. We know this is 2ty. We'll have to use a little bit of trig to come up with this ty in terms of the 10 newtons and the angle. Okay, so if you look at this, the sine of theta would be the opposite side. That's what we're looking for, divided by t, right? This is just the trig. Sine theta, that would be ty over t. So then t sine theta is ty. And I could take this and plug it in here for ty. So if I do that, I get 2 times t sine theta is f. And I know what t is from the picture over here. It's 10 newtons, right? So this would be 2 10 newtons sine theta. So finally 20 newtons sine theta. And then that's that's in the form of the answers that we saw before. Okay, but that's how you actually do the problem. It's kind of too tricky to make it as a voting question, I think, right? Because you've got to do more work than just kind of look at it. Okay, so that's where it's coming from. All right, good. Any questions on this one? So balancing forces. 100 kilogram block with the weight of 980 newtons hangs on a rope. Find the tension in the rope if the block is stationary, and then also if it's moving up at a steady speed of 5. Okay, so we know the mass of it is 100, the weight of it is 980. In the first scenario, it's just hanging there. In the second scenario, moving up with the speed of 5. Okay. Well, they tell us the weight is 980 newtons. And this is the one where it's just hanging around. This is tension. They do give us the mass. Okay, so just hanging around. This is just like the orangutan problem, right? It's not going anywhere, just hanging there. So if you got 980 down, you're going to have 980 up. So this is the one, again, where we're not even moving. Pretend you're trying to weigh something at the grocery store or something like that. Whatever you're hanging by a scale, whatever the weight of that is, it has to be equal to the scale reading. The same exact thing. Okay, that's the first part. So moving up with a steady speed of 5 meters per second. How much is the acceleration in that second part? I'll have to start bringing cookies in. Whoever gets it right gets a cookie. First, I'll have to bake some cookies. What do you think? How much is the acceleration if it's moving at a steady speed of 5? 0, right? It's not changing. There is no acceleration. Excellent. So this picture is the same, right? If the acceleration is 0, this is the same picture. So whether you're hanging around and not moving, or you're moving at a constant speed, it's the exact same scenario. Acceleration 0, those forces are equal to each other. Now, to get this to move in the first place, if it's just hanging there, the tension's got to be bigger initially, but we're just looking at what's going on after it's stopped accelerating and is moving at a constant speed. Okay, so same exact picture. All right. Well, a little tricky, but I think we're okay on that. So dynamics and Newton's second law. So now if you do have an acceleration, then we could actually use Newton's second law. So F is equal to ma. Add up all the forces. This is a kind of a command. And you get ma. Same thing over here for the y direction. So if you have an acceleration, you have to have a net force for that to happen. So a car with 1,500 kilograms of mass is being towed 20 degrees, a friction force of 320. So this is just like we had before so far. But what is the tension if the car goes from rest, from initial velocity of 0 to 12 in 10 seconds? So this one, we actually do have an acceleration. That's a difference here. We have an acceleration. We could figure out how much the acceleration is by using some kinematics. There's a motion diagram down there. We have acceleration. So if we do have an acceleration, we're going to have a net force. So similar, but now this is a dynamics problem. Okay, good. So kind of a synopsis of what I've just said. Now the free body diagram is also similar, but if you notice, the length of the tension vector is a lot bigger. The tension in the x has to be bigger than the frictional force. So here's tension in the x. It's bigger than the frictional force. That gives us a net force this way. Okay? So it's kind of a two-stage problem. Figure out the acceleration using kinematics, and then once we've done that, then we can figure out how much the tension has to be. Whoops. Okay, so let me switch to the other view here. Good. So you know how much you know what the free body diagram looks like. So horizontally, F is equal to ma. This is the part you have to supply. And again, we're going to have to go back and get the A part, but we can do that. It's just kinematics. So just to refresh your memory, normal, weight, friction, here's the tension, here's the X part, and then here's the Y part. So this